This is Swathi, working as Assistant Professor in Electronics and Communication Engineering Department in Institute of Aeronautical Engineering, Dundigal. Welcome to today's lecture. In this lecture, we are going to discuss about the registers and counters. So we'll be basically concentrating more on the registers and the various types of registers, that is the shift registers, and various modes of operation of shift register, and also universal shift register. So first of all, what is a register? So as we all know that flip-flop is a memory cell which can store one bit of information at a time. So if we want to increase the storage capacity, what we need to do? So if we need to increase the storage capacity, we need to cascade the flip-flops, and we need to cascade the flip-flops in a required number such that we can achieve the required storage capacity. For example, if we want to store 3 bits of data at a time, then we need to cascade 3 flip-flops together. If we want to increase the storage capacity to 4 bits, that means if I want to store 4 bits of data at a time, then I have to cascade 4 flip-flops that may be either of the type, that is either SR, JK or D or T flip-flop. So we have to cascade them. Then we can design a circuit that is capable of storing 4 bits of information at a time. And such a group of flip-flops is known as register, which can store multiple data at a time. So an n-bit register will consist of n flip-flops, and it is capable of storing an n-bit word. So the binary data in a register, so whenever we are storing the data, we can even move the data within the register from one flip-flop to the other flip-flop. And the register that allows the transfer of data from one flip-flop to the other flip-flop, that is the shifting of data from one flip-flop to the other flip-flop, is known as shift register. So the shifting can be done in either of the direction, that is either from left to right or right to left. So the register which allows the transfer of data or a shift of data from one flip-flop to the other flip-flop is known as shift register. And here, how the shifting operation can be done. So here, these registers are examples of synchronous sequential circuits which work in synchronous with the clock pulse. So here, the data stored in the register can be shifted 1 bit for every clock pulse applied. So that means when a clock pulse is applied, the shifting of one bit of information can be done in either of the direction, that is either from left to right or right to left. So this works in synchronous with clock pulse. So now let us see the shift register. So as we all know that the shift register is a type of register in which the data can be shifted from one flip-flop to the other flip-flop. And the shifting can also be done in either of the direction, that is from left to right or right to left. And hence, the shift register, we can have 2 types basically, that is shift left register and shift right register. So that is shift left register. So what does it mean? So when we are able to shift the data in the register from one flip-flop to the other flip-flop in the direction from left to right, then it is called as left shift register. If you are moving the data in right direction, that means one flip-flop to the other in the right to left, then it is called as right shift register. So here, basically there are 4 modes of operation based on the shifting. Either we can shift the data in left or in the right direction. So based on that, we can have 6 modes of operation here. We can have 6 modes of operation. So the first one is serial in, serial out. And we can have the second type, serial in, parallel out. And the third one is parallel in, serial out, parallel in, parallel out. and bidirectional shift register and universal shift register. These are the various types of shift register. Serial in, serial out shift register, serial in, parallel out, parallel in, serial out, and parallel in, parallel out. And next one, bidirectional shift register and universal shift register. So now let us see what is a serial in, serial out shift register. So here, as I said you that register is a storage device where we can store multiple bits of data at a time. So we need to first load the data into the register. So if the loading of data into the register is done in serial fashion, bit by bit, then it is called as serial in. Once the data is stored, we can also read the data from the register, right? So whenever you are reading the data from the register, if it is done again in serial manner, that is bit by bit, if we are able to read, then it is called as serial out. That means in a serial in, serial out register, the data is shifted in or else loaded into the register in serial fashion, and also data is read from the register in serial fashion, bit by bit. So this is the block diagram of shift register, where that is a serial in, serial out shift register. It is a 4-bit register where we can store 4 bits of data at a time into the register, and hence it is a 4-bit register. So as I told you that one flip-flop can store 1 bit of information. So as I want to store 4 bits of data, I have used 4 flip-flops here. So these are the 4 flip-flops. What is the types of flip-flops I have used here? D flip-flop, that is data flip-flop. So data flip-flops are most commonly used flip-flops in the construction of registers. So I have used flip-flops here, 4 flip-flops. So here this is a register which operates in, serial out. That means where the data is loaded into the register in serial manner, even the data is read from the register in serial manner. So here, now as I told you that, so we have used D flip-flops here, and this register is showing us a 4-bit serial in, serial out shift register in which the data can be shifted either to the left or right. So as we have taken data input at the leftmost flip-flop, so we can consider this as shift right register. We can consider this as shift right register. And we are taking the output from the rightmost digit. So this register is used to store, used to shift the data in the right direction, and it is an example of shift right register which is operating in, serial out fashion, serial in, serial out mode. If you want to convert it into shift left, then what should we do? We need to consider here D input, data input, and we have to take the output from the leftmost register, leftmost flip-flop. So that means I can convert this into either shift left or shift right. And the basic structure is working as a shift right register. If I want to convert it into shift left, I have to apply the input to the rightmost flip-flop and I have to take the output from the leftmost flip-flop. Then it will be converted into shift left. That is only the difference here. So I have taken 4 D flip-flops, and in which the data input is given to the leftmost flip-flop here, and the output is taken from the rightmost flip-flop. So here data input and the clocks are all connected to the clock inputs of all the flip-flops are connected to the same clock. So that is why it is called as synchronous. So if all the flip-flops are connected with different clocks, then it is said to be a synchronous register. But here it is synchronous. All the flip-flops are applied with same clock. So this is a synchronous, this is an example of synchronous sequential circuit. Now, and the data input is applied to the first flip-flop or else leftmost flip-flop, and the output of the flip-flop 3 is connected as input to the flip-flop 2. Next, similarly, output of flip-flop 2 is connected as input to the flip-flop 1, and the output of flip-flop 1 is connected as input to the flip-flop 0. So, and finally the output is read from the last flip-flop, that is flip-flop 0. So, Initially, whenever you are operating any sequential circuit, we need to reset the circuit. So, during the first clock pulse, what we need to do? We need to reset the flip-flop. That means we need to clear all the flip-flops here. That means the outputs of all the flip-flops must be made 0, 0. So, here, now, during the next clock pulse, so for example, what we need to do, I want to, as I told you, this is the operation. So first, all the flip-flops should be cleared or else reset, such that the outputs that are Q3 is equals to, Q2 is equals to, Q1 is equals to, and Q0 is equals to 0. And so here, this is about serial in, serial out shift register. Now what I want to do is, so during the first clock signal, what I'm doing? I'm clearing all the flip-flops so that the state of the register is 0, 0, 0. When we apply the clock, at this time, I want to store a data 1 into the first register. So, first of all, so here, now, what I'm doing, during the first clock pulse, we have just cleared the flip-flop so that the output is equals to Q3, Q2, Q1, Q0 is equals to all zeros. Now, when the next clock pulse is applied, so I want to send the data 1, so which is applied to the first flip-flop, that is D3, that is the leftmost flip-flop. So, D3 is 1. So, that means the data input I have considered as 1. So now what happens? Already 0 is stored in this one. This will be shifted. As I told you that the data will be shifted here, and that is why it is called as shift register. So during the clock pulse 1, so I am pushing the data 1 into the first flip-flop, that is the leftmost flip-flop, and the output of this flip-flop was 0 during the previous. That means as I have reset all the flip-flop, so it is 0. Now the 0 is pushed here. Now again this was 0, that will be pushed here, and 0 is pushed here, and the 0 is coming out. So that means now what I have read? I have read 0 here. Now during the next, that means what happened now? Now as the D input is 1, now the output of this flip-flop is 1, whereas this is 0, 0, 0. That means 1, 0, 0, 0 has been stored in the register during the first clock pulse. Next, during the next clock pulse, I want to, so that means I want to store all ones in the register here. All ones. So, now what I am doing during the next clock pulse, again I am sending D into the flip-flop here. So, already it was 1 here. So, now what I am doing, I am sending again 1 to the leftmost flip-flop. Already which is there, the 1 is there, that 1 will be pushed here. So as these are all D flip-flops here, as the input to this D flip-flop is 1, now the output again becomes 1. So what was the previous output? It was 0, it will be pushed here. So that is 0. Now again this 0 will be pushed here. So that means what is the output of the, what are the values of all the flip-flops here? 1 is stored in the first and second flip-flop, and the next flip-flops are 0, 0. That means the stored word now becomes 1, 1, 0, 0. Now during the next clock pulse, now what so 1, 2 bits are loaded into the register. Now I want to load the third bit. So during the next clock pulse, so now what happens? So you have to remember here, all the flip-flops are having bubbles near the clock. Means what? These are all the flip-flops which are working for the negative edge of the clock. That means falling edge. These are all called as negative edge triggered flip-flops. That means for every change or else transition in the clock from 0 to 1, the flip-flop changes its state. So now during the next clock pulse, I want to push the next one into the into the register here. Now D in is 1. Already 1 is stored here. That will be pushed here. And already 1 is stored in this one. That will be again pushed here. Now the output of this one is 1. And the 1 is pushed here. So already we have 0 in this one. That is pushed here. Now what is the value stored in this register? That is in the first flip-flop 1, second 1, and the third one is also 1. Whereas the fourth one is 0. So that means the data, the word stored in the register during the next clock pulse or is the third clock pulse is 1110. Now during the fourth clock pulse, now what happens? Again I am pushing 1. So already we have 1 here that will be pushed into this, and we have 1 here that will be pushed into this, and we have 1 here that will be pushed into this. So that means we have all ones now. So that means during the fourth clock pulse, we have we are now able to load all ones data in the shift register. That means in order to load the data, that is 111 or else 4 bits of data into the register, it required 4 clock pulses. It required 4 clock pulses. It was not done parallelly. We are loading the data bit by bit. So it requires 4 clock pulses. So now let us see the truth table of this. So here, as I told you that, so we have 4 flip-flops here. So D in, where it is the input, where it is given as the input to the third flip-flop, whose output is taken as Q3. And Q3 is given as input to the second flip-flop. So Q3 is equals to D2. And Q2 is given as the input to the third flip-flop. That is Q2 is equals to D1. And Q1 is equals to D0. And finally, Q0 will be taken as output. Okay, so now initially the flip register is cleared. So that means we made all the contents of the flip-flops as 0. And during the first clock pulse, as I told you, it is a negative edge. All the flip-flops are negative edge triggered. So we are considering the falling edge. Okay, so during this, 1 is pushed here. Whatever the data we have in the 0, that is pushed that is pushed here, and again we have 0 that is pushed here, and that is pushed here. So what is a word during the word that is stored in the register during the first clock pulse? That is 100. Now during the second clock pulse, again we are giving the input, and that will be stored in the leftmost flip-flop, and whatever the data we were having in the leftmost flip-flop, that will be now pushed into the second flip-flop, and the second flip-flop content is moved into third, and third flip-flop content is moved into fourth flip-flop. And similarly, this is the operation. Finally, we have loaded all ones in the register after how many clock pulses? 4 clock pulses. So that means even we can read the data bit by bit. So once we have loaded this, now the output is 0. Now 4 clock pulses are required for loading the 4 bits of data. Now in order to read the data, it is also done parallelly. So that means again in order to read, it is also done serially, bit by bit. So we cannot read all the data of all the outputs of all the flip-flops at a time. So we have to read them serially, bit by bit. So again, we require 4 more clock pulses to read the data bit by bit from the register, which is operating in, serial out mode. So this is a major drawback here. For loading it requires 4 clock pulses, and for reading also it requires 4 clock pulses. So that is time taking process. That means the propagation delay is more in, serial out. So now we'll see the next mode of so let us see the waveforms of serial in, serial out shift register. So we have 4 clock pulses, right? So this is the clock signal, and this is the data input. Okay, so initially it was 0 because we have cleared it. Now during the first clock pulse, that is a negative edge. So what we have done, we have considered the data input as 1. So now it will be pushed into Q3, and remaining all bits are 0, 0, 0. So initially 0, 0, 0, 0. So during the next first clock pulse, negative edge of the clock pulse, so we have pushed 1 into the first flip-flop. Next, during the negative edge of the second clock pulse, next what happens? So this one will be shifted here, and again we are pushing this one into this DN. So that is the third flip-flop is again loaded with 1, and whatever the data that was stored in D3 will be now pushed into D2. And again, so this is 110, and this one is 111. That means for all the 4 clock pulses, we can load all ones in the shift register. So that is about serial in, serial out. Now let us see the next mode of operation, serial in parallel. So serial in parallel shift register, in which the data is passed or else loaded into the register in serial manner, bit by bit, whereas we can read or else we can fetch the data from the register parallelly. That means we can read all the bits at a time. Okay, so here the data is loaded bit by bit, whereas the outputs are disabled as long as the data is loaded. So that means during the loading operation, the outputs are disabled. Once the data is loaded, we can read the data, all the bits at a time from all the flip-flops. So as soon as the data loading is completed, we can enable all the flip-flops so that the outputs are all read from all the flip-flops at a time. So that is why we are calling it as serial in parallel shift register. So that means here serial input. In order to store 4 bits of data, as we are going for serial in, so again it requires 4 clock pulses, whereas the output, once the data is loaded, we can read the data at a time. We can read the data all bits at a time. So that means within 4 clock pulses, the loading is done and also the reading is also done. So that is that means that the input operation is same as serial in serial out register, whereas the output operation is different, because in serial in serial out, even we are reading the data bit by bit, there we require 4 clock pulses, but here the in serial in parallel out, as we can read the data all the bits at a time, we can save some of the time. So that is why we can say that the serial in parallel out operation is faster when compared to the serial in serial out. So now let us see the circuit diagram of serial in parallel. So this is the block diagram for the serial in parallel register, shift register, which works in serial in parallel mode. Okay, so here again same thing. The clocks of all the flip-flops are connected to same clock. So again this is a synchronous sequential circuit. Whereas we are having one more input here. We can have clear or preset input, anything we can have. So what does it mean? If clear input is 1, so all the flip-flops will be cleared, irrespective of the input, irrespective of the other input, that is D. So whatever it is, if the clear input is 1, all the flip-flops will be cleared off. And here if you see the serial input, we are loading the data in serial fashion. So that is why we are connecting the serial input to the last flip-flop, that is the leftmost flip-flop, and the output of that leftmost flip-flop is connected to the second one, and the output of the second flip-flop is connected to the third, and the output of third flip-flop is connected as input to the fourth flip-flop. Whereas we have taken the output serially in case of serial in serial out, but we can take all the outputs at a time. So these are the parallel outputs, whereas this is the serial input. So this is the block diagram of shift register, which is operating in serial in parallel out. So even we have taken the input at the left side, so we can also consider this as shift right register, which is operating in serial in parallel out mode. Okay, so when the clock, as we are as we are applying same clock to all the flip-flops, we can say that this shift registers or else all the flip-flops will work in synchronize with the clock signal. That means same clock. And the we are using this parallel outputs for reading the output from the register, all the bits at a time. So now let us see the operation. So in this parallel in serial out, so this is about a serial in parallel out. So even if you want to load the data, first 1 bit that will be shifted here during the next clock pulse. So during the first clock pulse, the data will be 100. This is during the first clock pulse. Next, during the second clock pulse, what will be the data? So if I push the 1 here, then this 1 will be coming here, the 0 will be coming here, this 0. This is during the second clock pulse. During the third clock pulse, again I am pushing 1 here. So now already 1 we have in the last flip-flop, which will be shifted, and 0. This is the word that is stored during the third clock pulse. Next, during the fourth clock pulse, 1 again I am loading 1 here. So this 1 is loaded, this 1 is shifted here, this 1 is shifted here. That means what we are doing? We are shifting the data in the right direction. So that is why it is right shift register which is operating in. Once the data is loaded, we can read the data from all the flip-flops at a time using the parallel output. So this is serial in parallel out register. Now the next one is parallel in serial out register. So as the name itself indicating, parallel in serial out. That means we are applying all the inputs parallelly at a time, whereas the output is read bit by bit serially. So this is why it is called as parallel in serial out register. And the circuit diagram I'll be showing. So in this case, this is the circuit diagram here. So other than flip-flops, we also have some logic circuit in order to perform the parallel in serial out operation. So here now, so this is a logic circuit or else block diagram for the shift register which is operating in parallel in serial out mode. So here D flip-flops we have taken 4 D flip-flops. So and all the clocks the flip-flops are applied with same clock pulse. Now we have some logic circuit here, AND gates followed by OR gates, AND gates followed by OR gate. So before that we have a control input, that is shift or load. For example, if this shift or load is equals to 0, what operation it performs? Either load operation or shift operation. We'll see now. If it is 0, so this line becomes 0, whereas this line becomes 1. So if you observe this connection, so all the AND gates which are odd numbered. So 1, 3, 5. So 1 is connected to 0, 3 is connected to 0 and 5 is also connected to 0. So that means all the logic gates 1, 3 and 5 will be disabled because one of the inputs to this AND gates are 0 now. So now what happens? These are all disabled. Now remaining even numbered logic gates and AND gates, those are applied with 1, 1, 1. Right? So now 2, 4, 6 are enabled here. 2, 4, 6 are enabled here. So now the other input as this one input to this AND gates is 0. So 1, 3, 5 or the outputs of 1, 3, 5 logic gates are 0. Now these are enabled, and here now if you see the leftmost flip-flop is applied with B0. Okay, and the next flip-flop is applied with, so here as this is enabled, B1 is connected here. Now it is 0. 0 plus B1 is B1. So B1 is applied here. Next, here as this is 0 and this is one of the other input to the fourth logic gate, fourth AND gate is B2. So B2 is applied here. Next, this is B3. So B3 is applied here. So that means what happens when shift or load line is equals to 0, it performs parallel loading. So once it is B4, B0, B1, B2, B3. So the inputs to the flip-flops are B0, B1, B2, B3. So that means when shift or load is equals to 0, it performs the parallel loading operation. So here in parallel in serial out shift register, we can have two modes of operation. Either it can shift the data or it can load the data parallelly. Okay. So now what happens if it is equals to 1? If it is equals to 1, now this line becomes 0 and this line becomes 1. So now what are the logic gates that are enabled here? 1, 3, 5 will be enabled now and 2, 4, 6 will be disabled now. Now let us see what are the inputs to the odd numbered gates here. So the output of first flip-flop is given as input to the first AND gate. Next again the output of second flip-flop is given as input to the third AND gate. And the output of this flip-flop is given as input to the, and this one we can take it as output. So now what happens? So here the data already stored in this one. Let us consider this is 1, 0, 1, 0. So now 1 will be shifted here and 0 will be, because this is 1, right? It is a D flip-flop. So now we have already 0. Now that will be coming here and 0 will be shifted here and the 1 is there. So now see the connection here. So along with this will be shifted here. Okay, so that means initially it was 1010. Now during the clock pulse, what has happened here? This has shifted this position and this position. Okay, and here we will be placing 0. So this is the word stored in the next clock pulse. Sorry, this is 1. This is 1 here. 0 1 0 1. Okay, so like that it shifts the data in the left direction. It shifts the data in the left direction. So this is paralleling serial. So that means we can perform two operations, that is load and shift. So when the shift or load bar line is set to 0, then second, fourth, sixth AND gates are active. Hence the bits B0, B1, B2, B3 are passed to the correct respective flip-flops. That means loaded. Next, the binary inputs B1, B0, B1, B2 and B3 will be parallelly loaded into the respective flip-flops when there is a change in the clock. That is, again we are considering the negative edge triggered flip-flop. So when there is a change in the clock from 0 to 1, 1 to 0, definitely the data will be loaded into the flip-flops at a time parallelly. So next, shift mode. What happens when shift or load bar line is set to 1? So then opposite action takes place. That is, second, fourth and sixth gates are inactive now and 1, 2, 3 gates are active now. So this performs the shift of data in the right direction. Okay, so at this time the first and fifth gates are activated and the shifting operation will be done from left to the right. So that is about parallel in serial or shift register. Next, let us look at the parallel in parallel out. The other mode of operation, parallel in parallel out. That means we are able to load the data all bits at a time parallelly, and even we are able to fetch the data from the register all the bits at a time, and hence we are calling this register as parallel in parallel out shift register. Now let us see the structure of that. Before that, so here we are going to cascade all the flip-flops at a time, where all the flip-flops are applied with same clock. Again we are considering negative edge triggered flip-flops. So that means all the flip-flops will be changing its state during the negative edge of the clock. So here, now let us see the structure of this shift register, which is operating in parallel out mode. So we have 4-bit shift register which operates in PIPO mode. So in which all the flip-flops are connected to the same clock, and we are applying all the flip-flops with different data B3, B2, B1 and B2. That means all the flip-flops are loaded with binary data parallelly at a time. So these are the parallel inputs. These are the parallel inputs, and whereas we can also read the data parallelly by using this parallel outputs. So this is simple structure. Inputs all at a time and parallel outputs. So this is a faster mode of operation, because within a clock pulse we can even load the data and we can even read the data from the register, one clock pulse. So this is faster. Now let us see the bidirectional shift register. So bidirectional shift register. So as I already told you that in a shift register, even the data can be shifted from one flip-flop to the other flip-flop, either from left to right or from right to left. So if it is shifting the data from left to right, then that register is called as right shift register. If the data is shifted from right to left, then that register is said to be left shift register. Right. Here, bidirectional shift register is the one in which the data can be shifted either from left to right or from right to left. So whereas we can observe that in a left shift register, we cannot shift the data from right to left. Only we can shift the data from left to right. But here, if in a register, if you can shift the data both in left to right and right to left directions, then that register is said to be bidirectional shift register. So now let us see what happens when we are shifting. So when a binary number is shifted by each bit, that means when we are shifting the binary number, that means each bit of the binary number to the left by 1 bit position, then it will be equivalent to the number produced by multiplying the original number by 2. Let us consider 0, 1, 1, 0. This is my number. Now I am performing left shift operation by 1 bit position. So when I perform left shift operation, this 0 will come here, and this 1 will come here, and this 1 will come here, whereas this 0 will be coming here. So this is the right shift. Now let us see, this is nothing but right shift, and let us see left shift operation. Okay, so now left shift. So here this 1 will come here, this 1 will come here, and this 0 will come here, and LSB will place 0. So this is nothing but left shift. Okay, so this 0 will come and sit here. That means whenever we are performing left shift, so this bit will be shifted here, whereas this bit will be shifted here, 0 will be shifted here, and the LSB is placed with 0. Whereas in the right shift operation, so 0 is shifted to the next bit, 1 is shifted to the next bit, 1 is shifted. So what about the MSB? We need to place 0 in the MSB. So what is the actual decimal equivalent of this number? 2, 6. What is the decimal equivalent of this number? 3. So that means when I perform a right shift operation, that means when I shift each bit of a binary number by 1 bit position to the right, then it indicates, or else it results in a number which is equivalent to the division of that number by 2. So 6 by 2 is what? 3. Whereas whenever you are performing the left shift of a number, that means whenever you are shifting each bit of a binary number 1 bit to the left position, then it results a number which is multiplying the original number by 2. So what is the original number here? 6. 6 into 2 is 12. What is the decimal equivalent of this one? 12. So that means when you perform the left shift operation by 1 bit position, it will be equivalent to the number produced by multiplying the original number by 2. If you are performing the right shift operation, then it will be equivalent. That means if you are shifting by 1 position, right shifting by 1 bit position, then it will be equivalent to the number produced by dividing the original number by 2. So that is, you have to remember. So that means in order to perform the arithmetic operations such as multiplication and division, we will be using this shift register. So in order to perform this multiplication and division, we need to shift the data either to the left or to the left. If you are shifting the left, then we can perform the multiplication operation. If you are shifting to the right, then we can perform the division operation. So that means in such cases, we need to be able to shift the data in both the direction from left to right and right to left. And for that we need a register, and such a type of register which can shift the data in both the directions is called as bidirectional shift register. So this is the block diagram of bidirectional shift register. Okay, so where we can perform shift left as well as shift right operation. So these are the 4 flip-flops which are cascaded together, which are applied with the same clock. That means all the 4 flip-flops are applied with the same clock here. And we do also have clear input. When the clear input is 1, then all the flip-flops will be cleared. That means all the flip-flops will be 0. That means the outputs of all the flip-flops will be 0. Along with this D flip-flops, we have some AND OR logic. Okay, now let us see how it operates. Okay, so here we have one control input, shift or load bar. Okay, and we have 2 more external inputs here, input DR and input DL. So this is used for performing the right shift operation, and this is used for performing the left shift operation. Okay, now let us see what happens if this shift or load bar output is 1, okay, or 0. When it is 0, what happens? Which AND gates are enabled and what will be the output of each flip-flop? We'll see now. So when it is 0, so as I told you that this is a bidirectional shift register. So we can perform the shift operation either from left to right or from right to left. Now we'll see how it is shifting the data from left to right and left to right. Now for that, let us consider this control input as 0 here. That means this line is 0. This is connected to all the AND gates, odd AND gates. 1, this is 3, 5, 7. That means all the AND gates numbered or with the odd numbered or disabled now. Whereas this is an inverter which produces output as 1. So where all the even numbered gates are connected to 1 now. So now 2 is enabled, 4 is enabled, 6 is enabled and 8 is enabled now. So now what happens? As 1, 3, 5, 7 are disabled, so this will be disabled here. This will be disabled here. Whereas this is enabled now because this is connected to the 8th AND gate. So now this DL, this is a left shift bit. Okay, left shift data input. So now it will be given as input to the D0. Okay, if I consider this as 1, this will be 1 now. What was the output of this one? Initially, we will clear all the flip-flops. So this was 0. So this 0 was given to, let us see the directions here. This 0 is given to 6th gate. Okay, so now what is the output of this 6th gate? 0. And this is given as here. So now the output is 0 and previous output was 0. That will be given here. And now, okay, that will be given here. That will be pushed into this. Okay, that means it is 0. Again, now the previous data is again given to this. That will be pushed here. That means what is happening here? The data is moved from right to left. So that means when the shift or load control input is 0, it performs the left shift operation. That means the data is shifted from right to left. That means it performs the left shift operation. Now let us consider, I will just indicate that one with green color. So now let us consider this as 1. Now this will be 0. If this is 0, now all the even numbered gates are disabled and odd number gates are enabled. Okay, so as odd number gates are enabled, so now I am applying DR here. So now DR will be pushed into D3. So whatever the data that is 0 here, so now the data is pushed to the next flip-flop. Now this is given as input to the next flip-flop. So now whatever the data that is 0 here, now again that will be pushed to 5th flip-flop. Okay, and this will be pushed here. Now how the data is moving? From left to right. Okay, so now again whatever the data that is stored in this flip-flop will be going to the, okay, now this data will be going to the 7th flip-flop and 7th AND gate. This will be pushed here. Okay, so that is how we can do the right shift operation. Sorry, left shift operation. Sorry, it is moving from left to right. That means right shift operation. How the data is moving? To the right side. So we can see that it performs the right shift operation when shift or load control input is 1, and it performs the left shift operation when shift or load input is equals to 0. So this is how it performs the shift operation. So that when m is equals to 1, it performs the right operation. When m is equals to 0, it performs the left shift operation. Okay, so again, so in order to load the data, either in the left shift mode or right shift mode, again we require 4 clock pulses because we are applying data serially. We have only one input. If you look at this one, if you look at the circuit, do we have any parallel inputs here? We don't have any parallel inputs. So we can simply take the output from Q0 here. If it is right shift, we can take the output from this flip-flop. If it is left shift, we can take the output from this one. If it is left shift. Okay, so that means we can only read or load the data serially, but we can perform the shifting operation in both left and right direction. That means we can shift the data from left to right or right to left. So that is why it is called as bidirectional shift register. I hope it is clear. Now let us see the universal shift register. This is the last type of shift register. We have universal shift register. So what do you mean by universal shift register? When a register is used to shift the data in only one direction, either it is from left to right or right to left, then it is called as unidirectional shift register. When we can shift the data in both the direction, that is from right to left and left to right, then we can call that register as bidirectional shift register, as we are able to shift the data in both the directions. Now, universal shift register. What is this universal shift register? So, this is another type of shift register in which we can load the data in a parallel way and also shift the data in both the direction, that is from left to right and right to left. Such a register is called as universal shift register. That means what we are doing in the universal shift register, we can perform parallel loading and also we can perform left shift, right shift operation. So till now we have seen SISO, SIPO, PISO and PIPO and bidirectional. So what we have done with all the first four modes, we are able to either load serially or parallelly, and we in that all the cases we are able to either shift the data in left or right direction. But in the bidirectional shift register, what we have seen, we can shift the data from left to right as well as from right to left. But there also the data can be loaded and read from the registers in serial fashion. Okay, so that is why it is called only bidirectional shift register. Now I want a register in which I can perform the parallel loading as well as I can shift the data in either of the direction from right to left or left to right. So that can be done by universal shift register. So let us see the definition of universal shift register again. So universal shift register is a register in which we can load the data in a parallel way and also we can shift the data in either of the direction, that is from left to right or right to left. So that is called as universal shift register. Now let us see the design of an universal shift register, and the construction of universal 4-bit universal shift register can be done with the help of multiplexers and flip-flops. I hope you all know the multiplexers. What is a multiplexer? Which is having 2 per n inputs and 1 output, whereas any one of these 2 per n inputs can be selected by n selection inputs, right? So this is about multiplexers. So now we are going to use the multiplexers and flip-flops in order to design a 4-bit universal shift register. So let us see the operation of, this is the universal shift register in which we have 4 D flip-flops. These are the 4 D flip-flops, and we do have 4 4x1 multiplexers. So in a 4x1 multiplexer, what is the number of selection inputs we have? 2 selection inputs. So if we have 2 selection inputs, what are the possible combinations we can have? 4 combinations, 0, 0, 0, 1, 1, 0, 1, 1. Based on this selection inputs, this shift register can operate 4 modes. Can operate in any of the 4 modes. What are the 4 modes here? When the selection inputs are 0 and 0, it performs no change operation. That means it just holds the data. It just holds the data whatever it was stored in the register. Okay. When the selection input S1 is equals to 0 and S0 is equals to 1, then it performs right shift operation, and 1, 0, it performs left shift operation, and 1, 1, it performs parallel loading. Now let us see whether it is correct or not with respect to this circuit. We'll see now. Now this is the circuit here. First let us understand the connections here. So these are the flip-flops. So we have clear input here. So we have an inverter. That means it is a negative clear input. That means when the clear input is 1, this all will be disabled. Whereas when the clear input is 1, it becomes 0. Then what happens? All the flip-flops will be cleared off. Sorry, when the clear input is 0, then it becomes 1. So if the clear input is 1, which is applied to the D flip-flop, so then all the flip-flops will be cleared. And we have a clock here. So we do have a negative, that is a inverter. That means it indicates negative edge triggered flip-flop. Negative edge triggered flip-flop. So here, this is about flip-flop here. And now let us see all the flip-flops are applied with same clock here. And we do have 4 multiplexers, and all the 4 multiplexers are applied with same selection input. So this connection indicates that all the multiplexers are applied with same selection input. Now let us see, here we have 4 lines M1, M2, M3, M4, which are said to be parallel inputs, and we do have 4 lines which are F1, F2, F3 and F4, which are said to be parallel outputs. And we do have 2 extra inputs here, serial input for shift left operation and serial input for shift right operation. Now let us see the connection here, 0, 0, when a selection inputs 0 and 0. So as we all know that when the selection inputs are 0 and 0, then 0th input line will be selected and it will be sent to the output here. So that means, so 0th line will be selected here. So here also this 0th line. So this 0th line of the rightmost mux is connected to the, just a second. Okay, so 0th line. So whatever the data that is stored in this one is given to the D here. This is given to the D input of the flip-flop. And the output is given here. Okay. And next, again it is 0. So this is connected to 0. And this is 0. Again the third flip-flop is connected to the 0th input of mux. This is 0. This is connected to the mux here. So here, now what happens during the serial input 0, 0, there is no change in the condition. It all stores the data or whatever, it retains the same data here. Now let us see what is happening here. So here, let us see, this is F1. F1 is connected to 0th input. When the selection inputs are 0 and 0, so this F1, which is the output of first flip-flop, is connected here. This is 0. Okay. And this is again given as input. Okay. And this is given here. Now, what about this one? This 0 input is connected to the F2. Okay. So again, this is given as output here. That means what is happening? Is there any change? The same data is again loaded here. This 0 input is connected to the F3. Whatever the data that was stored in the flip-flop, that was again given as input here. So now again, this F4 is given as input to the 0. So that means whatever the data that is already stored in the flip-flop, again given as feedback. So that means, is there any change in the case? Is there any change in the content of the flip-flops? No, the same data is again loaded into the data. So that means it holds the previous state, whatever it was in. That is about 0, 0. Now let us consider, let us change the color, red. Now let us consider, so here S0 is 1 and S1 is 0. That means when the selection inputs are 0, 1. So in that case, one input will be selected and this will be connected to the output. Now, one input is connected, one input of this first flip-flop is connected to what? Serial input for right shift. Okay, so this is connected here. Okay, now whatever the data that was previously stored, okay, whatever the data that was previously stored, let us consider this as 1 here. Now it is loaded with 1. Already the output was 0. Now it was given as input to the first input of the second mux. So now as this line is selected, so what is the data we have got here? 0. Now this will be pushed here, 0. And this is connected again back to the first in. Okay, so now again this is pushed here, and whatever the data that was there in this in this flip-flop will be shifted this, and this will be coming as up. So that means what is happening when 0 1, what kind of operation is performed here? The data is shifted from left to the right. That means the data is shifted in the right direction. So that means it performs the right shift operation. Now let us see what happens. Now let us take another color, blue color. Now let us take, this is 0 and this is 1. Now which one is selected here? 2 is selected. What is the binary decimal equivalent here? 2. 2 means this line is selected here. So if you see this 2, so this 2 is connected to the serial input for shift left. So now this 2 will be sent as input to this one. Okay, whereas the output is again given back to the second input of the second marks. So now as this is selected, so this will be coming here, right? So now this will be coming here and coming as input here. Now this line will be selected and it will be given as input. Now whatever the data that was stored in this one will be taken and it will be applied to the second input. And now again this is applied here, and whatever the data that is stored in the flip-flop will be now connected as input, second input to the marks, and this will be taken. So like that. So what is happening here? Whenever the selection inputs are 1 and 0, it is performing. How, in what direction it is, the data is shifted from this to this to this to this. It is shifting in the left direction. So that means when the selection inputs are S1 is equals to 1 and S0 is equals to 0, it performs the left shift operation. Now let us consider when both are equals to 1 and 1. When both are equals to 1 and 1. Now what happens? Third line will be selected. So third lines of all the multiplexers are connected to the parallel inputs M4, M3, M2, M1. So that means this data will be loaded into the multiplexer and which are connected to the flip-flops here. So now all the data will be applied parallelly. So that means what is happening? When selection inputs are 1 and 1, parallel loading operation is done here. So that is what about the operation of universal shift register. Only the thing is you need to remember the connections of flip-flops and multiplexers so that you can analyze the output. When the selection inputs are 0, 0, there is no change. Whatever the data that was stored in the flip-flops during the previous clock, that will be retained as it is. So that is why no change operation or else hold state. It holds the data. Next, when the selection inputs are 0 and 1, it performs the right shift operation. That means the data is shifted from left to the right. When the selection inputs are 1 and 0, it performs the left shift operation. It will be shifted from serial input for left shift input to the rightmost. And when both the selection inputs are 1 and 1, it performs the parallel loading operation. So this is about the operation of universal shift register, where we can use this for parallel loading and for shifting the data in both the direction, that is from left to right and right to left. I hope it is clear. Next, so this is about shift register and various modes of operation of shift register, and what is a bidirectional shift register and universal shift register. Now let us see the applications of shift register. So here, first of all, if you go through the parallel in serial out shift register, so where the data is taken in parallel and the output and the data is read from the register in serial fashion bit by bit. So this finds more applications in parallel to serial converter, where it converts the parallel data into serial, where the data input is given in parallel fashion, whereas the output is taken in serial fashion bit by bit. And this kind of operation can be most commonly used at the transmission section of an analog to digital converter. Whenever we are designing analog to digital converters, which converts an analog signal into digital, So there we can find the applications more for a parallel in serial out shift register. And similarly, serial in parallel out. What is the serial in parallel out mode of operation of a shift register? Where we have a data input, where we can load the data into the register serially bit by bit, whereas the data can be read from the register parallelly all the bits at a time. So this finds more applications even in the communication at the receiver section while converting the data from digital to analog. Inverse operation of A to D converter. So that means whenever we need to convert the data from digital to analog, we are always using DAC block. While using this DAC block, we are going to prefer the serial to parallel shift register. And similarly, we can find one more application of a shift register, that is in case of sequence generator. So what is this? Shift register along with some additional gates generate the sequence of zeros and ones, and which we can use for generating any required sequence, and hence we can find the application of shift register in sequence generator also. And the last and most important application of shift register is it can be used as counter. So here we can have two types of counters. We can design two types of counters using shift register. One is the ring counter and Johnson ring counter, or else twisted ring counter. So here, based on the connection of flip-flops, we can design two types of counter. What is a counter basically? It counts the events. That means the occurrences of pulses, it can count. So the counter is a sequential circuit which counts the occurrence of an event, or else which counts the pulses in a clock. Okay, so here we can even design two types of counters using shift register. These are the major applications of shift register. Those are ring counter and Johnson ring counter. So which are basically based on the connection provided from the rightmost flip-flop to the leftmost flip-flop. So that we'll be studying in further classes. So these are the major applications of shift register. So those are we can use in the design of analog to digital converters where we need parallel to series converter. And similarly, we can find the shift registers, we can find many applications of shift registers in, again in communication in order to design digital to analog converters block. And even we can use it for sequence generator, and even for the designing of counters, which are Johnson counter and ring counter. So that's all for today. That's all for this lecture. Thank you one and all. I hope it is clear to everyone. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.